Hi everyone, my name is Claire Tomlin and I'm a professor in electrical engineering and computer sciences at Berkeley. And this is a series of modules that we've been developing to support the course EE221A, Linear System Theory at Berkeley. This module is module 12 in this series, and the topic is singular value decomposition. In the last module, we defined what we meant by singular values of a matrix, and we defined that based on our previous development of Hermitian matrices and unitary matrices. So now let's actually use this concept of singular values to present, we're not going to prove it in this module, but we're going to present a very useful decomposition of matrices, which is going to come up as we develop further modules into linear system theory. So this is just a presentation of that decomposition. If you have a matrix A, and in general A has elements in the field which is either the real numbers or the complex numbers. So generally, let's assume that A is an m by n dimensional matrix, and let's assume that its elements are complex numbers. And let's assume that the rank of A is equal to R, where R is less than or equal to the minimum of m and n. Then the theorem about singular value decomposition states the following. So theorem. There exist unitary matrices, and we'll call them U and V, and we remember the definition of unitary matrices. A unitary matrix is one in which a matrix U such that U star times U is equal to UU star, which is the identity. Of course, U star U and UU star may be of different dimensions, but that product is the identity matrix in the appropriate dimension. So here, in singular value decomposition, we have a matrix U, which is an m by m dimensional matrix, and a matrix V, which is an n by n dimensional matrix, such that A can be decomposed into the product of three matrices, U, sigma, V star. Sigma is an m by n dimensional matrix. It's of the same dimension as A, and then U and V are square matrices of these dimensions. So the product is an m by n dimensional matrix, and the product is A. Sigma is a matrix. It's a diagonal matrix, which looks as follows. The upper left part of A is a square matrix. We're going to call that sigma R. It's a diagonal square matrix whose diagonal elements are they're related to the singular values of A. And then we have zero matrices that make up the m by n dimensional matrix. And here, so sigma R is a diagonal matrix. We write that as diagonal matrix whose elements are the singular whose diagonal entries are the singular values of A, sigma 2 up to sigma R. In fact, the diagonal entries are the non-zero singular values of A. Okay, so this is, and remember R is the rank of the matrix A. And the rest of the matrix sigma is equal to 0. Now, so the theorem states, and this is the theorem that we're not going to prove, but it states the existence of such unitary matrices, U and V, such that A can be decomposed into this form. And it's this form that turns out to be very useful as we use this further in linear system theory. We can say a few more things about this decomposition. So we can think more about the structure of U and V. So let's actually go back to the top and write, let's break down U and V according to sigma here. So U, I'm going to represent as two matrices. So U1 and U2. And so what this means is that, so we remember that U is an M by M dimensional matrix. U1 is the first, so U1 is the first R columns of the matrix U, and U2 is the remaining M minus R columns of the matrix U. Okay, so U1 has M rows and R columns, so it's M by R, and then U2 has M minus R columns. Okay, and then V, I'm going to represent V similarly in terms of its column space as matrices V1 and V2. And again here, V1 is going to be an N row by R column matrix, and V2 will be an N row by N minus R column matrix. And so if we break those, and right now this is just a naming convention, but you can start to see why we're doing this, because now if we look at the representation of A in terms of the multiplication of U, sigma, and V, this multiplication, post-multiplication of U by sigma is going to just pull out the piece of U that multiplies sigma, because the rest will just be multiplied by corresponding the zero elements in that sigma matrix. And so with that theorem, we can break this down and break that decomposition down into the following. That A is equal to U sigma V star, and that's just going to be U1 sigma R V1 star. Okay, and we remember star is consistent. It's the complex conjugate transpose of that corresponding matrix. Okay, so U star U is, so U is a unitary matrix. So U star U is an M-dimensional matrix. We know that V star V is going to be an N-dimensional matrix. If we look at U1 star U1, so U1 star U1, just those first R columns of the matrix U, we can easily show that that's an R-dimensional matrix, and then similarly V1 star V1 is an R-dimensional identity matrix. That just comes from the fact that these matrices are unitary. Okay, so now if we look at the matrix AA star, then that's what I'm going to do is just I'm going to take that breakdown, that decomposition, and multiply it by its complex conjugate transpose. So that's going to be U1 sigma R V1 star U1 times U1 sigma R V1 star star. And then we bring the complex conjugate transpose inside that product, which reverses the order and applies the complex conjugate transpose. And then using these properties we've just derived, we can quickly break that down or show that that simplifies to U1 sigma R squared U1 star. Okay, so then if we look at AA star times U, or AA star times U1, so let's just post-multiply that product by U1, that's just equal to U1 sigma R squared. And if we think about this matrix U1 now, we further break that down. So those R columns into, we just think about that matrix as M rows, and then there's R columns. Let's call the R columns of U1. So let's call U1, so let's use a little bit of an abusive notation, but little u1, little u2, up to little ur. Those represent the columns of the matrix U1. Then we can just see from this breakdown that the columns, the first R columns of the matrix U1 represent the some kind of eigenvector relationship of the matrix AA star with respect to these eigenvalues of AA star, which are sigma r squared, which are the are the singular values of the matrix A. So these columns, U1, U2, up to UR, are called the left singular vectors of the matrix A. Left singular vectors. So they're the left singular vectors associated with the singular values of the matrix A. Similarly, you can look at A star A, and using the same kind of breakdown that we did here, we can write A star A, and so we apply the same steps, and let's not write it out. You can try that. But A star A, VI, so if we look at the first R columns of the matrix V1, and we call those V1, V2, V3, up to VR. So now I'm just going to write it simply as VI, which represents the columns of the matrix V1, then that's equal to sigma I squared VI. And so these are called the right singular vectors. Right singular vectors associated with the singular values of the matrix A. Right singular vectors of A. Okay, so that's really all I want to say in this module. I've just presented the singular value decomposition of the matrix A. We've presented a theorem about the existence of this decomposition and basically what this decomposition is, that there exists these unitary matrices such that the matrix A, not necessarily square, can be written in terms of a product of these three matrices where one of the matrices is a special form that contains a diagonal matrix with the non-zero singular values of the matrix A. Okay, so we have the existence of such a decomposition, and then we can look at some of the nice structure of that. Given the properties, given the fact that these are unitary matrices, we can use that property and break it down and define what we mean by left and right singular vectors of the matrix A associated to its singular values. So we'll stop here, and as I said, we'll be using this singular value decomposition of matrices as we go further into the course. Good. Thank you very much.